This video shows how to analyze and interpret passive scalar data from a Barracuda virtual reactor simulation. Using a variation of the Kuiper's training problem, we will introduce a passive scalar pulse at an inlet flow BC and use Tecplot for Barracuda to analyze the output data. A passive scalar can be thought of as a tracer fluid that follows the flow field, but does not affect the physics of a simulation. Therefore, it is useful for determining the residence time distribution of fluids. In this example project, we've already defined a passive scalar BC, which must be in the same location as a flow BC that introduces fluid into the system. In this case, we have a uniform flow BC at the bottom of the system, so we have placed our passive scalar BC in the same location. We've used an SFF file to create a pulse of the passive scalar from 1 to 1.1 seconds. This is how we recommend setting up passive scalars, so that you can clearly compare the input pulse to the output flux plane data that records when the scalar leaves the system. In this example, we've defined one pulse, but it can also be useful to define several pulses separated by some amount of time for longer running simulations. We've already run the solver for this example, so now we can plot the passive scalar data from the flow BC and pressure BC. To do this, launch Tecplot from the post-run window. Click on File, Load Barracuda Data, Load Data File. Select the flow BC flux plane, in this case flux BC inlet. Double-click on the line to bring up the mapping style dialog. Deselect Show Map in the first row and select it for the row with the map name Time Integration of All Scalars Crossing Flux Plane. Use Ctrl F to autoscale the plot. In order to view the pulse, you will need to find the derivative of this data. To do this, click on Data, Alter, Specify Equations. In the Equations box, type the following text: curly bracket pulse, curly bracket, equals ddx, parentheses, curly bracket. The name of the data row needs to be input here, and it has to be exactly correct. So click on Dataset Info and double-click on the correct line and copy the text. Close the Dataset Information dialog and paste the text into the equation. Close the curly brackets and parentheses and click on Compute. Return to the Mapping Style dialog and double-click on the y-axis variable for the plot. Select the new data created in Pulse and use Ctrl F to autoscale the plot. The pulse of the scalar at the inlet BC is now shown. To add the data from the outlet pressure BC, use the Load Barracuda Data dialog, Load Data File, Flux BC Outlet. In the Mapping Style dialog, click on Create Map. Select the y-axis variable for the passive scalar and make sure you've highlighted Zone 2. Once the new map is created, return to Specify Equations dialog. Select Zone 2 to alter, add a negative sign in front of the derivative in the equation to account for Barracuda's sign convention where anything leaving the system is negative, and click Compute. Now double-click in the y-axis variable column for the new map and select Pulse. Both the inlet and outlet peaks will be shown on the plot. Change the map name to identify each line. Click on Plot, Line Legend, select Show Line Legend. The time between the peaks corresponds to the average residence time of fluid in the system. The outlet flux plane signal for the passive scalar is stretched out in this example, indicating that there is a range of fluid residence time in the system. The flow of a passive scalar can also be shown visually. Start with View Results from the Barracuda GUI and switch to a 3D view of cells fluid pressure. Double-click on the color bar and in the drop-down, select Scalar 0. Load all files by clicking on File, Load Barracuda Data, and selecting All for Tecplot files to load, and clicking on Refresh Reload. Then play through all solution times to see the passive scalar pulse pass through the system. It is often useful to have this kind of visualization in conjunction with the XY plots discussed previously to get a full understanding of the information provided by passive scalars. This concludes our video on analyzing passive scalar pulse data.